This is the Boeing B-17F Flying Fortress. More than a symbol of American air power, the B-17 was a large-scale engineering solution to a specific problem: how to deliver heavy bomb loads deep into enemy territory, in daylight, under sustained fighter and anti-aircraft attack. During World War II, the B-17 became the backbone of Allied strategic bombing over Europe. It was designed to fly long distances at high altitude, operate in tight formations, and absorb significant battle damage while remaining controllable. The aircraft earned its reputation not because it was invulnerable, but because its structure, redundancy, and defensive systems allowed crews to survive conditions that would destroy lighter bombers. Flying the B-17 came at a high cost. Daylight bombing exposed crews to intense flak and coordinated fighter attacks, resulting in severe losses, especially before long-range fighter escorts became available. Yet through those losses, the B-17 shaped the tactics, formations, and operational doctrine that defined the Allied air campaign and ultimately contributed to the defeat of the Axis powers. In this film, we take a technical look inside the B-17F variant. We examine how it was built, how it was operated, and how its design balanced firepower, survivability, and range under wartime constraints. This is not a legend. It is a machine. My name is Marcus Reed, and this is Iron Blueprint. At first glance, the outer skin appeared thin and fragile, typically around 1/50th of an inch thick, but it functioned as a load-bearing element, rather than simple aerodynamic covering. This stress skin approach allowed the aircraft to distribute aerodynamic and structural loads across the fuselage and wings, reducing overall weight while maintaining strength. Beneath the skin, the fuselage was reinforced by a network of formers and longerons that defined its shape and absorbed bending forces during flight, turbulence, and combat damage. The wings were more complex structurally. Each wing used a multi-spar layout, with twin longerons supported by internal trusses. Corrugated aluminum sheeting added stiffness beneath the outer skin, increasing resistance to flexing under heavy bomb loads and high-G maneuvers. Control surfaces, including ailerons, elevators, and rudder, were fabric-covered to save weight and reduce control forces. In terms of size, the B-17F was substantial. The fuselage measured just under 75 feet in length, stood over 19 feet tall on the ground, and featured a wingspan of nearly 104 feet, comparable to modern narrow-body airliners. Empty weight was approximately 34,000 pounds, while standard maximum takeoff weight was around 65,000 pounds. In extreme cases, aircraft could launch at weights approaching 72,000 pounds, pushing the airframe close to its structural limits. The fuselage was assembled in numbered sections, each designed as a modular unit to simplify production, repair, and maintenance. At the front, Section 41 housed the plexiglass nose, bombardier station, and navigator position, with provisions for multiple forward-firing machine guns, depending on configuration. Section 42 contained the flight deck, including pilot and co-pilot stations, primary flight controls, and instruments. A dorsal turret was mounted above this section, operated by the flight engineer. Section 43 formed the bomb bay, occupying the center of the aircraft and carrying the majority of structural load between the wings. Behind it, Section 44 included the radio compartment and the ball turret installation beneath the fuselage. Further aft, Section 46 served as the waist gunner area, with open waist windows on either side. Early B-17F configurations placed these windows directly opposite each other, creating cramped working conditions and occasional interference between gunners during combat. At the rear, Sections 47 and 49, known collectively as the Stinger, housed the tailwheel assembly, rudder and elevator control systems, and the tail gun position. Section 48 completed the empennage, including the large vertical stabilizer and rudder that provided directional stability. The result was an airframe optimized not for speed or elegance, but for durability. The B-17F was designed to remain structurally intact despite localized damage, a philosophy that prioritized mission completion and crew survival over aerodynamic efficiency. The bomber functioned as a coordinated system, where failure in one position could compromise the entire crew. The aircraft commander was the pilot. He was responsible for overall control of the bomber, formation flying, engine management during combat, and final decision-making in emergencies. The pilot rarely worked alone. The co-pilot served as the executive officer of the aircraft. He assisted with navigation, engine monitoring, and checklist procedures, and was expected to assume full command immediately if the pilot was wounded or incapacitated. The flight engineer occupied a dual role. He monitored engine performance, fuel consumption, and electrical systems alongside the pilots, while also maintaining responsibility for several defensive weapons. From his position, he operated the dorsal turret armed with twin 50 caliber machine guns. The navigator was responsible for keeping the aircraft on course throughout the mission, using dead reckoning, radio beacons, airspeed, wind estimates, altitude, and celestial navigation. He continuously calculated the bomber's position from takeoff to target and back. During combat, the navigator could also man a forward gun in the nose section if required. The bombardier held one of the most critical positions on the aircraft. His sole task was the accurate delivery of bombs on target. During the bombing run, aircraft control was temporarily transferred to him through the bombsight system. He also operated forward-facing defensive guns mounted in the nose. The radio operator maintained long-range communication with base and other aircraft in the formation. In combat, he could deploy a 50 caliber machine gun mounted in the roof of his compartment to engage attacking fighters. Defensive firepower was further provided by dedicated gunners. The ball turret gunner operated a remotely isolated spherical turret beneath the fuselage, defending the aircraft from attacks from below. Two waist gunners were positioned on either side of the fuselage, engaging fighters approaching from the flanks. At the rear, the tail gunner manned twin 50 caliber machine guns, serving as the last line of defense against pursuing enemy aircraft. Each crew member relied on intercom communication and strict discipline. Warnings were issued using a clock-based call-out system to identify enemy approach directions. Coordination and timing were essential, especially when multiple gunners engaged the same target. The B-17F crew was not a collection of individuals. It was a tightly integrated human system, operating under extreme stress, altitude, cold, and enemy fire. The aircraft could absorb damage, but only teamwork allowed it to fight, navigate, and return home. Protect the crew and critical systems from fragments rather than stop direct heavy caliber hits. The aircraft used thin manganese steel armor plates mounted on rubber padding. These plates were distributed throughout the fuselage in key crew stations, including the cockpit, bombardier position, radio compartment, and gunner stations. The armor was primarily intended to defeat shrapnel from anti-aircraft artillery and small caliber fire. It offered limited protection against 30 caliber rounds, but was not capable of reliably stopping direct hits from larger cannon shells. Given the extremely thin, stressed duralumin skin of the B-17F, armor coverage had to remain selective. Excessive armor would have increased weight beyond acceptable limits and reduced range and altitude performance. To compensate for limited armor, operational tactics were critical. When flying through flak zones, pilots were instructed to vary course and altitude at regular intervals to disrupt enemy firing solutions. This reduced the probability of shells detonating at the correct altitude and position. In formation flight, however, evasive maneuvering was restricted. Individual aircraft could not maneuver freely without risking collision, forcing crews to rely on discipline and coordinated movement by following the lead bomber. The armor of the B-17F reflected a deliberate engineering compromise. It did not make the aircraft invulnerable. Instead, it reduced the likelihood of catastrophic crew casualties while preserving the range and payload required to reach deep strategic targets. The aircraft was designed to carry its payload internally, allowing it to retain a relatively clean aerodynamic profile, despite its size. Under optimal conditions, the B-17F could carry up to 9,600 pounds of bombs. This typically consisted of 8 1,000-pound bombs mounted in the central bomb bay. External underwing pylons existed in theory, but were rarely used, as they significantly increased drag and reduced range. Bomb load selection was a critical part of mission planning. At maximum payload, the aircraft's effective combat radius was severely limited. For most long-range missions, crews carried between 4,000 and 6,000 pounds of bombs, allowing a combat range of roughly 1,300 to 1,400 miles. All bombs were suspended vertically, in the bomb bay, on electrically released racks. This configuration allowed rapid and simultaneous release while maintaining aircraft balance during the drop. Defensive armament defined the Flying Fortress reputation. The B-17F was equipped almost entirely with 50 caliber M2 Browning machine guns, chosen for their reliability, stopping power, and effective range. Gun positions varied by production block and field modification. Standard defensive layout included twin 50 caliber guns in the dorsal turret, twin guns in the ball turret, twin guns in the tail position, single guns in each waist window, and additional guns in the nose and radio compartments depending on configuration. Unlike later variants, the B-17F lacked a chin turret. This made frontal attacks particularly dangerous, as enemy fighters could exploit the relatively weaker nose defense during head-on approaches. A key tactical advantage of the B-17 was formation defense. When flying in tight box formations, overlapping fields of fire multiplied the number of guns covering every approach angle. This created dense defensive zones that were difficult for single-engine fighters to penetrate without sustaining damage. The armament system of the B-17F was not designed to win dogfights. It was designed to deter attacks, break up enemy formations, and force fighters to disengage before delivering sustained fire. In iron blueprint terms, the B-17F was not a bomber protected by armor. It was a weapons platform protected by geometry, coordination, and the sheer volume of defensive fire. The targeting system of the B-17F was built around one principle. Precision bombing from high altitude required mechanical accuracy, not pilot judgment. As the bomber approached the target area, control of the aircraft was partially transferred from the pilot to the bombardier. This was achieved through an autopilot linkage connected to the Norden bomb site. During the bombing run, the aircraft flew straight and level. This steady flight profile was essential for accurate bomb release, but it also made the B-17 highly vulnerable to anti-aircraft fire. The Norden bomb site was a stabilized optical system combined with a mechanical analog computer. It used gyroscopes to maintain a fixed reference point, allowing the bombardier to track a target despite aircraft movement. Before the run, the bombardier entered several variables into the system. These included altitude, true airspeed, wind speed, wind direction, and target bearing. The bomb site continuously calculated the required release point based on these inputs. Once engaged, the bomb site could make small corrective inputs to the aircraft's heading through the autopilot. In effect, the bombardier temporarily steered the bomber during the final approach. When the target aligned with the bomb site crosshairs, the bombardier released the bomb load electrically. At that moment, he announced the command "bombs away," signaling the pilot to regain full control. From an engineering perspective, the Norden system represented one of the most complex mechanical targeting solutions of the war. It relied entirely on gears, cams, and gyroscopes, rather than electronics or computation. Operationally, the system was only as accurate as the conditions allowed. Cloud cover, flak, evasive maneuvering, formation disruption, and human error often reduced effectiveness. Despite its limitations, the targeting equipment of the B-17F defined Allied daylight bombing doctrine. It transformed the aircraft from a simple bomb carrier into a precision delivery system built around mechanical calculation under fire. The B-17F earned its nickname Flying Fortress primarily because of its defensive armament. Rather than relying on speed or maneuverability, the aircraft was designed to fight its way through enemy airspace using overlapping fields of fire. The defensive system was built almost entirely around the 50 caliber M2 Browning air-cooled machine gun. This weapon offered a balance of range, stopping power, and reliability that made it ideal for bomber defense. In the B-17F configuration, guns were distributed to cover nearly every approach angle. The goal was not to make the aircraft invulnerable, but to make any attack costly and dangerous for enemy fighters. The ventral defense was provided by the ball turret. This remotely powered turret housed two 50 caliber machine guns and was mounted beneath the fuselage. It covered the lower hemisphere of the aircraft, an area especially vulnerable to attack. Above the fuselage sat the dorsal turret. This turret was also armed with twin 50 caliber guns and was typically operated by the flight engineer. It provided coverage against fighters attacking from above and slightly behind, At the rear of the aircraft, the tail gunner operated another twin 50 caliber installation. This position was critical, as many enemy fighters preferred to attack from directly behind where closing speed was lower. Along the waist section, two single 50 caliber guns were mounted on opposite sides of the fuselage. These waist guns defended against lateral attacks and filled gaps between the forward and rear firing arcs. In the nose, armament varied by configuration. Early B-17F aircraft carried lighter weapons, but later versions added additional 50 caliber guns to strengthen frontal defense. Individually, none of these gun positions guaranteed protection. Their true strength came from coordination and overlap. When flying alone, a B-17 was vulnerable. When flying in formation, the defensive armament of multiple aircraft merged into a dense web of fire. This concept transformed formations into moving gun platforms. Enemy fighters were forced to fly through concentrated streams of tracer fire simply to reach firing range. Defensive armament on the B-17F was not designed to chase or destroy fighters outright. Its purpose was to deter attacks, disrupt aim, and break up coordinated enemy assaults. In engineering terms, the Flying Fortress was not armored enough to ignore damage. Instead, it relied on firepower, redundancy, and formation tactics to survive missions deep into hostile airspace. To understand how aircraft like the B-17F were actually flown and fought, one effective way is through simulation. War Thunder provides a large-scale combat environment that recreates the operational limits of World War II aircraft. In War Thunder, the B-17 Flying Fortress appears as part of the United States bomber development line. Players experience the same constraints faced by real crews, including limited maneuverability, high exposure to enemy fighters, and dependence on defensive fire rather than speed. One key feature relevant to the B-17 is formation flying. Multiple bombers can operate together, recreating overlapping defensive fields of fire that defined real daylight bombing tactics. Survivability increases, not through individual performance, but through coordinated positioning and discipline. The simulation also highlights trade-offs faced by bomber crews. Heavier bomb loads reduce range and climb performance. Higher altitude improves survivability but increases exposure time to flak and interceptors. War Thunder allows players to operate bombers, fighters, ground vehicles, helicopters, and naval units within the same combat environment. This makes it possible to see how air power, ground defense, and interception tactics interacted as complete weapon systems. From an iron blueprint perspective, the value is not spectacle. It is systems understanding, how aircraft were designed to be used, where they were strong, and where they failed. Experiencing these constraints firsthand helps explain why formations mattered, why escort fighters became essential, and why aircraft like the B-17 could not survive alone deep over enemy territory. As combat experience accumulated, both Allied and Axis pilots began to understand the limits of the B-17 defensive system. The sheer number of machine guns created intense psychological pressure on attacking fighters. Streams of tracer fire forced enemy pilots to react defensively even before accurate fire could be delivered. German fighter units quickly learned that attacks from directly behind or from high angles exposed them to multiple overlapping gun positions. Losses during these approaches were heavy, especially in 1942 and early 1943. As a result, Luftwaffe tactics evolved. Head-on attacks became increasingly common. Approaching from the nose reduced exposure time and limited the number of guns that could engage before the high closing speed forced separation. Communication inside the B-17 was critical. Gunners used a clock direction system to report threats. 12 o'clock indicated straight ahead. 6 o'clock meant directly behind. High and low calls specified vertical position. When a warning was called out, turrets and waist guns would reposition immediately. The goal was not precision marksmanship, but volume of fire. Defensive fire was intended to disrupt aim, damage aircraft, or force attackers to break away. Only the dorsal and ball turrets were equipped with reflector sights. Most other gunners relied on simple iron sights or fixed reference points. Accuracy depended heavily on experience and coordination. Formation density created another problem. In tight combat boxes, fields of fire often overlapped with friendly aircraft. Friendly fire incidents were not rare, especially during chaotic engagements under heavy attack. Despite these dangers, the defensive armament achieved its purpose early in the war. It inflicted losses, it delayed attacks, and it forced enemy fighters to adopt riskier tactics. However, defensive fire alone was never enough. As German fighter numbers increased and tactics improved, the limitations of bomber self-defense became clear. From a systems perspective, the B-17 defensive armament was formidable, but not decisive. It was designed to buy time, not to guarantee survival. The B-17F Flying Fortress was powered by 4 Wright Cyclone R-182097 radial engines. Each engine was a 9-cylinder air-cooled radial designed for durability rather than outright speed. In standard operation, each engine produced approximately 1,200 horsepower. Under wartime emergency power, output could be briefly increased to around 1,380 horsepower, at the cost of accelerated wear and higher failure risk. Each engine drove a 3-bladed constant-speed propeller with controllable pitch. This allowed pilots to optimize thrust during takeoff, climb, cruise, and combat conditions. A critical feature of the B-17 engine system was the use of exhaust-driven turbo superchargers. Mounted remotely from the engines, these units compressed intake air at high altitude, allowing the engines to maintain power well above 25,000 feet. This capability was essential for daylight bombing missions over Europe. Engine management was complex and required constant attention. Pilots and flight engineers monitored manifold pressure, cylinder head temperature, oil pressure, and fuel flow continuously. Improper settings could quickly lead to overheating or detonation. If an engine was damaged or caught fire, the crew could shut it down and feather the propeller. Feathering rotated the blades parallel to the airflow, dramatically reducing drag and allowing the aircraft to continue flying. The engines were numbered 1 through 4 from left to right as seen from the cockpit. Procedures were standardized so that crews across thousands of aircraft could operate and troubleshoot systems under stress. In theory, the B-17 was capable of sustained flight on 2 engines. In practice, combat damage to wings, fuel lines, or control systems often made this impossible. Some aircraft returned home on a single engine, but these cases were exceptional. From an engineering standpoint, the B-17 engine system emphasized redundancy and survivability. It sacrificed speed and efficiency in exchange for reliability, altitude performance, and the ability to absorb damage. The engines did not make the Flying Fortress fast, they made it persistent. The fuel system of the B-17F was designed around redundancy, balance, and long-range endurance. Fuel was carried primarily in the wings, distributed to support both structural strength and flight stability. In its standard configuration, the B-17F used 6 main fuel tanks. 3 tanks were installed in each wing. Engines 1 and 4 were supplied by a single tank each, while engines 2 and 3 drew fuel from 2 tanks per side. This layout ensured that the loss of a single tank would not immediately disable an entire wing. It also allowed fuel consumption to be managed in a way that minimized lateral imbalance during long missions. Fuel transfer between wings was possible using an electric pump system. This allowed the crew to rebalance the aircraft if fuel usage or damage caused uneven weight distribution. To extend range, the B-17F could be equipped with additional auxiliary fuel systems, known as Tokyo tanks. These consisted of 18 self-collapsing rubber tanks, 9 installed in each wing. The Tokyo tanks did not have dedicated pumps. Instead, they relied on gravity to feed fuel into the main wing tanks as fuel was consumed. Their placement helped distribute weight evenly across the wings during maximum range missions. With Tokyo tanks installed, fuel capacity increased by approximately 1080 gallons, added to the standard 1,700 gallons carried in the main tanks. For missions where range was prioritized over bomb load, an additional auxiliary tank holding around 820 gallons could be installed in the bomb bay. In this configuration, total fuel capacity could exceed 3,600 gallons. This allowed deep penetration missions, but at the cost of reduced bomb load and increased vulnerability. The main fuel tanks were self-sealing. They used a layered rubber structure encased in a metal shell. When punctured, the gasoline-reactive rubber expanded and sealed the hole, greatly reducing fire risk. The Tokyo tanks lacked a metal outer shell and were more vulnerable to damage. Under combat conditions, vapor buildup inside these tanks could turn them into serious fire hazards. From an engineering perspective, the fuel system reflected the B-17 design philosophy. Range and survivability were prioritized, even when this introduced complexity and risk. The Flying Fortress could go far, but every additional mile carried a cost in weight, vulnerability, and crew workload. The B-17F was engineered with a clear separation of responsibilities between hydraulic and electrical power. This division reduced system complexity and improved survivability when damage occurred. The hydraulic system was intentionally minimal. It powered only two critical functions, the wheel brakes and the cowl flaps used for engine cooling. By limiting hydraulic dependence, designers reduced the risk of total system failure caused by leaks or battle damage. Wheel braking relied on hydraulic pressure generated by engine-driven pumps. If hydraulic pressure was lost, braking effectiveness was severely reduced, making landing hazardous, especially on short or damaged airfields. Cowl flaps were also hydraulically actuated. These adjustable panels controlled airflow over the engines, allowing crews to regulate cylinder head temperature during climb, cruise, and combat power settings. In contrast, the electrical system was extensive and central to the aircraft's operation. Electrical power was generated by engine-driven generators, meaning that as long as at least one engine was running, the aircraft could maintain electrical function. The electrical system powered the landing gear, wing flaps, bomb bay doors, gun turrets, and most cockpit instruments. It also supplied power to radios, navigation equipment, intercom systems, and internal lighting. Because electrical reliability was critical, the B-17F included battery backups and an auxiliary gasoline-powered generator located in the tail section. This auxiliary unit provided emergency power for radios and essential instruments if engine-driven generators failed. From an engineering standpoint, this approach reflected wartime priorities. Hydraulics were kept simple and limited. Electric systems carried the operational burden, but were supported by redundancy and multiple power sources. The result was an aircraft that could continue flying, fighting, and communicating even after sustaining significant damage. In the B-17F, systems design was not about elegance. It was about staying operational when conditions were already going wrong. Navigation aboard the B-17F was one of the most demanding and technically critical tasks of any bomber in World War II. Despite a crew of 10, only 3 officers were primarily responsible for getting the aircraft to the target and back: the pilot, the co-pilot, and the navigator. The navigator's role was central. He was responsible for determining the aircraft's position over vast distances, often with no visual reference to the ground and under constant threat from weather, flak, and enemy fighters. Navigation relied on a layered system rather than a single method. Dead reckoning formed the foundation. By calculating heading, airspeed, time, wind drift, and altitude, the navigator estimated the aircraft's position continuously throughout the mission. Radio navigation provided additional reference points. Radio beacons and directional signals helped confirm position when signals were available, though jamming, atmospheric interference, and range limitations often reduced reliability deep over enemy territory. Celestial navigation was also used, particularly on long-range missions. Using a sextant through dedicated observation ports, the navigator took star and sun readings to calculate position. This method required clear skies and intense concentration, often while wearing heavy gloves and oxygen equipment. Landmark recognition became important during the final phases of a mission. Rivers, coastlines, cities, and rail junctions were used to verify position. But smoke, cloud cover, and camouflage often made this difficult or impossible. All navigation data was plotted manually on maps. There were no computers, no digital corrections, and no automation. Every correction depended on human judgment and constant recalculation. A navigation error of only a few degrees could cause a bomber stream to miss its target entirely or drift into unexpected enemy defenses. Fuel planning, formation timing, and bombing accuracy all depended on the navigator's precision. In the B-17F, navigation was not a background task. It was a continuous engineering problem solved in real time by one man. using instruments, mathematics, and experience while flying through hostile airspace. Starting the engines of the B-17F was a carefully choreographed mechanical procedure that required coordination between multiple crew members and strict adherence to checklist discipline. The process began with electrical power. The pilot activated the master switch, bringing the primary electrical system online. The co-pilot then engaged the battery switches and inverters, confirming stable voltage for engine start and instrument operation. Attention next shifted to hydraulics. The parking brakes were set and verified, ensuring the aircraft remained stationary during engine ignition. Booster pumps were checked to confirm adequate hydraulic pressure for braking control. Fuel system checks followed. Fuel quantity was verified across all wing tanks, and the appropriate tanks were selected for engine start. Carburetor air filters were opened to allow unrestricted airflow into the engines. The 4 Wright Cyclone engines were started one at a time, usually in numerical order from engine 1 to engine 4. Each engine start followed the same sequence. Fuel flow was introduced, the starter engaged, and ignition applied at the correct moment to avoid flooding or backfire. As each engine came to life, the crew closely monitored oil pressure, engine temperature, and revolutions per minute. Any abnormal readings required an immediate shutdown to prevent engine damage or fire. Once all 4 engines were running, the crew conducted a full instrument check. Vacuum pressure for flight instruments was verified, and the radio operator powered up the communication equipment to confirm readiness. The engine run-up phase followed. With brakes locked, the pilot increased power to test magnetos, propeller pitch control, and turbo supercharger response. Generators were checked and briefly taken offline, then re-engaged to ensure reliable electrical output. Before taxi, final adjustments were made. Trim tabs were set, the tailwheel lock engaged for directional stability, and gyroscopic instruments aligned for navigation. Starting the B-17F was not a simple act of turning a key. It was a systems check of the entire aircraft. Only when every engine, pump, generator, and gauge behaved exactly as expected was the Flying Fortress considered ready to leave the ground. The B-17F Flying Fortress was not defined by any single innovation. It was the product of structural redundancy, mechanical discipline, and a design philosophy that prioritized survival under sustained damage. From an engineering standpoint, the aircraft was conservative rather than elegant. Its airframe relied on proven stressed skin construction. Its systems were intentionally redundant, often heavier and less efficient than necessary, but resilient under combat conditions. The B-17 was not built to evade enemy fire. It was built to endure it. Operational experience revealed both the strengths and the limits of this philosophy. The belief that defensive firepower alone could protect bomber formations proved costly in the early years of the air war. Only with long-range fighter escort did the Flying Fortress achieve its intended effectiveness. Mechanically, the aircraft demanded discipline. Engine management, fuel balancing, formation flying, and navigation required constant coordination between crew members. Success depended not on speed or maneuverability, but on teamwork and procedural precision. By the end of the war, more than 12,000 B-17 seconds had been produced. Thousands were lost in combat, yet many more returned home bearing damage that would have destroyed lesser aircraft. This durability became the foundation of its reputation. The B-17F was not the most advanced bomber of the Second World War. It was not the fastest, the highest flying, or the heaviest armed, but it was reliable, survivable, and structurally honest. In iron blueprint terms, the Flying Fortress stands as a lesson in wartime engineering reality. Victory was not achieved through perfection, but through systems that continued to function when everything else failed.